Alright guys, so today is going to be a pretty long lesson. We've got actually a lot of different things to look at. Some of it is based off of what we did yesterday though. But before we get started, I just want to look at some kind of overarching basic things to make sure you guys understand some of the vocab we talk about here. So when we talk about numbers, there are a lot of different sets of numbers that numbers can belong to. We're going to go over a couple of those just because you'll hear those names come up today. So the first set we're going to look at is what's called our natural numbers. And if you look at this chart below, it lists those as well. So that N with that fancy font, that's just a general way of writing the set of all natural numbers. So natural numbers are just your basic counting numbers like 1, 2, 3, 4, etc. 72, 35. Any normal counting whole positive number is a natural number. The next set is what that Z is for. And even though it doesn't have a Z in it, integers is my next set. So integers include all of the natural numbers, but they also include 0 and all the negative numbers, but they are still whole numbers. So the next set is, it's denoted by Q, but those are going to be our rational numbers. And rational numbers we're going to talk about today. So rational numbers are basically any number that can be made with a fraction. Okay, any number that can be made using a fraction. So it could be a decimal, like 0.75 is a rational number because it can be written as a decimal. So any fraction, any integer, any whole number, those are also rational numbers, positive or negative. An example of something that is not a rational number, though, would be something like the square root of 3 or pi. Those are not rational numbers because there's no way to write that number perfectly as a fraction. There may be a fraction close, but it's not actually an equivalent. And the last set of numbers we have are real numbers. And real numbers include basically everything except for those imaginary numbers you guys learned about in Algebra 2. So real numbers is the biggest set, which goes around everything, and it counts all the other sets plus anything else we might have missed. Okay, so now that we've talked about those two sets, today we're going to look mostly at our real numbers and our rational numbers. And the first one we're going to talk about is rational numbers. And we're going to learn something about called the rational zero theorem. So we use the rational zero theorem to find all of the possible rational zeros of a polynomial. Not every rational zero it has, just the possible ones. And again, these are only the possible rational zeros. So if the square root of 2 was a solution, we wouldn't find that using this. And what we're going to do is it's written as P over Q. P are the factors of the constant term, and Q are the factors of the leading coefficient. So we're going to use that in an example, help it make a little bit more sense. So the first thing we need to find is P. And P are the factors of the constant term. So those are going to be the factors of 8. So numbers that multiply to 8, some factors, I've got 1, 2, 4, and 8. Those are all factors of 8. But other factors are also -1, -2, -4, and -8. So I can do positives or negatives always for both of these. So now my next one, I need to find the factors of 4. So my Q's are going to be factors of 4. And those are plus or minus. I'm going to write it that way to save some space. Plus or minus 1, plus or minus 2, and plus or minus 4. So now once I actually have all those numbers, what I'm going to do,
Teachers, if you have not eaten,
my P's, I'm going to use a different color. P's over Q. So I'm going to take every P and divide it by every Q. So all of these, just to make it a little bit shorter, these will all be plus or minus. And I'm just going to write it once to save myself a little bit of time. So what the easiest way to make sure I include all of these, what I like to do is I start with one P, so I'll start with 1, and I'll do 1 divided by each Q. So I'll do 1 over 1, 1 over 2, and 1 over 4. Now you guys all know 1 over 1, that's the same thing as just 1. Now I go to my next Q. Okay, so another option I have 2 as a P value. I have 2 divided by 1, 2 divided by 2, and 2 divided by 4. 2 over 1 I'm just going to write as just 2. 2 over 2, that's 1, which I already have written up there. I don't need to write it again. And 2 over 4 we know is 1/2. I already have that. I don't need to write it again. So then I move on to my next P. The next P is 4. So I could do 4 over 1. 4 over 2 is 2, which I already have. 4 over 4 is 1, which I already have. Then I move on to my last P value, and that's 8. So I have 8 divided by 1, which is just 8. 8 divided by 2 is 4, I already have it, and 8 divided by 4 is 2, which I already have. So these are all of the possible rational zeros I could have, both positive and negative for both of these. Again, not necessarily every one of these will be a 0, but any rational 0 that I find for that polynomial would be one of those numbers. So then this is where it takes to take a little bit more time. We're going to use that rational 0 theorem to do something similar to what we did yesterday. It's going to be a little bit more time intensive. So what we're going to do is we're going to factor this polynomial. Now if you try to factor this by grouping, I wouldn't be able to, because I wouldn't be able to get any common groups here. So since I can't factor it by grouping, I'm going to factor it using the method we used yesterday. But what made yesterday's method easier is it told you the number to start with. In this case, we don't know what number to start with, so we have to find a number that's going to work. So in order to do that, I need to find the possible rational zeros. And I'm going to do that by finding my p's over q's. So first thing, I'm going to find my p-values. Okay, so as we learned already, the p's are the factors of the constant term, which is 6. So the p's that are possible are 1, they're plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Then I also have to look at the possible q's. So the possible q's are the factors of the leading coefficient, which is 2. So my possible q's are plus or minus 1 and plus or minus 2. So now once I have my p's and q's, just like we did in the last example, each p divided by each q. So these possibilities are plus or minus 1 over 1, 1 over 2, and then I'm going to move on and do each p. So the next one would be 2 over 1, 2 over 2 I already have, I've got 3 over 1, and then I've got 3 over 2, then I have 6 over 1, and 6 over 2 is 3, which I already have. So these are all the possible rational zeros I could have. So that means I'm going to pick one of these to start off with. Now it doesn't matter what number you pick, but what I'm going to do is I'm just going to pick some random number, let's do 3, and I'm going to do synthetic division with that number. So I'm going to set up synthetic division, I've got my number in the box, I'm going to try and see if 3 works. So if 3 works, x minus 3 is a factor. So I'm going to write my coefficients, and I'm going to do synthetic division. And I know this is going to work if I get 0 for a remainder. And I did not get 0 for a remainder, I got 30 for a remainder. So that means that 3 is not a 0 of this equation. X minus 3 then is not a factor. So I don't have to worry about that one anymore. Now it could still be negative 3, but let's just try a different number. Let's try 2. So let's do 2, 1, negative 13, and 6, and I'm going to do synthetic division all over again. And this time, I got 0 as a remainder. So what that means is that 2 is a 0, which means that x minus 2 is a factor. So now I just need to find the remaining factors of this polynomial. And those remaining factors are going to be taken from the equation I have left over. So now I just need to factor this last part. So that yellow part I can factor. I can do this the same way. Multiply 2 times negative 3, negative 6. I need two numbers that multiply to negative 6 and add up to 5. So those numbers are going to be a positive 6 and a negative 1. And now I can factor by grouping. So I take out my 2x, take out my minus 1. And this yellow part is going to factor into 2x minus 1 and x plus 3. And I still have that original, which is x minus 2. So that's how this whole thing factors out. So that also means even if I didn't pick 2, it saves you a little bit, because I know this also, synthetic division also would have worked with negative 3, and it also would have worked with a positive 1/2. So my 3 rational zeros are 2, negative 3, and 1/2. So this is how we use that rational zero theorem to factor questions we haven't done before. So it is a little bit of a long process, but alright, so now what we're going to do is instead of finding the rational zeros, we're going to find all of the real zeros. So in order to do that, we're going to start off the same way. We're going to start off making this a little bit simpler. We can't factor it as it is. Always try to factor first, because that is the easiest way to do it. But since we can't factor this question as is, we need to simplify it a little bit using that same method we just used. So if I find all of my possible p over q values, the p values I have are my factors of 12, which are 1, 2, 3, 4, 6, and 12. And then my possible q's are just 1. And these are all plus or minus, don't forget that. So that's going to make it really easy to find my p over q's, because the only value I have to divide by is 1. So that means my p over q values is just plus or minus 1, 2, 3, 4, 6, and 12. So I'm going to pick one of those to start off with, and I'll just pick number 3. It'll save you guys a little bit of time. So I'm going to do synthetic division with 3. So I'm going to write my coefficients. And I end up getting 0 as a remainder. So since I have 0 as a remainder, that means that x minus 3 is a factor, which means that 3 is one of my zeros. Now I don't need to write the factor because this question is just asking to find the zeros, not the factor. So 3 is one of my zeros. Now if you look, the polynomial I'm left with is x squared minus 2x minus 4. And if I try to factor this, I actually can't, because there are no numbers that multiply to negative 4 that add to negative 2. So I need to solve this quadratic equation some other way. Now it tells me just to find the real zeros, not necessarily the rational ones, which means my answers could have a square root of them, which means I can't factor it. There's two methods I could use to solve a quadratic equation. I can do the quadratic formula, or I can complete the square. And it is up to you which method you want to use, depending on whatever's going to be easiest. I'm going to go ahead and do the quadratic formula just because you've had practice with that for a little bit longer. So the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So what I'm going to do is I'm going to fill in those values. So starting with my negative b would be 2 plus or minus the square root of b squared minus 4 times 1 times negative 4, and that's all divided by 2 times 1. And now I can just simplify that square root. I have 2 plus or minus the square root of 20 divided by 2, and I can continue to simplify this a little farther because I can simplify that radical. Now one thing to be careful of right now, I can't just take those 2's and divide them out. That doesn't work, because if you remember, every term at the top has to have that 2 on it before I simplify it. What I can do is simplify the square root of 20. That can break down into 2 square root of 5. And now, because every term has a 2 in it, I can break that down into 1 plus or minus the square root of 5. So my 3 zeros then are 3, 1 plus the square root of 5, and 1 minus the square root of 5. So if a question asks you to find the real zeros, start the same way with your rational zeros theorem. But if you end up getting a quadratic equation that you can't factor, remember there's other ways to solve quadratic equations. So use one of those other methods to solve that. Alright, so now we've got 2 more things to look at that are a little bit new, different rules. And the next one is Descartes' rule of signs. Now this one's pretty simple to do. You just have to remember how it works and what we can use it for. So Descartes' rule of signs is what we use to find the number of real zeros that are possible. It's not going to give us the exact number, but again, it's going to give us some options here. So the first one we look at is the number, to find the number of positive real zeros, we look at the number of sign changes. Okay? So by sign changes, that's simple. If you look at this example down here, I go from a positive, I move that instead of writing on it. If I look at this one, I go from a positive to a negative, that's 1 sign change. Negative to a positive, that's 2, that's 3, and that's 4. So there's 4 sign changes, which means there could be 4 positive real zeros. But then it has this other part thrown in here where it says it also can be a multiple of 2 less. So basically, once you find your number, you subtract 2 if you can. So my answer could also be minus 2, it could also be 2, or it could be 0. That's actually also a possible option. Alright, so let's try another one looking for positive zeros. Let's look at 3x cubed plus x squared minus 7x plus 1. So if I look, this very first is positive, the next one's positive, that's not a sign change. But then that's a sign change, and that's a sign change. So the number of possible positive real zeros is 2, or remember I can subtract 2, it could also be 0. Now the next part, it says we also can find the number of possible negative real zeros. So what that is, that's the number of sign changes of p of negative x. So I work it out the same way, but what's different is I need to plug in negative x. So to find this one, it's 7 times negative x to the 6th power minus 4 times negative x to the 4th plus 3 times negative x squared minus 2 times negative x plus 1. And now I can simplify this a little bit. Now what's important here to realize is if it's an even power like 6, that negative x is still going to be positive. So nothing's going to change from my original equation if it's an even variable. But what is going to change would be my next term. This minus 2 times negative x, that would actually become a positive 2x now. So once I have that simplified, I still need to find the number of sign changes. So I still go from positive to negative to positive, but now the next one is not a change, and the next one is not a change. So for negative answers, that is only 2, or still 0. Alright, so if you want to look at one more, let's look at that second equation we wrote, but let's make that a negative x and see what that does. So what that's going to do is that's going to change my original equation. Now that original equation is going to be a negative 3x cubed, still plus x squared, but now plus 7x plus 1. And what that does, if I look at my sign changes now, there's negative to positive, there's 1. That's the only sign change I have. So the only possible negative zeros, there's only could be 1. So remember, Descartes' rule of sign is only used to find the possible number of real zeros. It doesn't tell us what they are, just how many there possibly could be. Alright, now the last thing we're going to look at is, again, it's pretty simple if you remember how to use it. Basically, we're going to find upper and lower bounds. In order to find upper and lower bounds, all you need to do is synthetic division. So if you know how to do synthetic division, you already know how to do this. It's not too bad. Okay, just remember that that's all we need to do. So if I do synthetic division, if I can prove that a number is an upper bound if I do synthetic division and my quotient and remainder are all positive numbers. I can prove something is a lower bound if I do synthetic division with Q or R and my quotient and remainder alternate signs. So let's say I have a function. Okay, let's say I have the function x squared minus 2x plus 1, and I want to prove that 3 is an upper bound. Okay, so I'm going to prove that 3 is an upper bound. The way I'm going to do that is I'm going to do synthetic division with 3. So 3 goes in the box, I write my coefficients, and then I do my synthetic division. And if you look, my quotient, which is x plus 1, and my remainder are all positive numbers. So since they are all positive, I just proved the work is your answer here. So this work is what proved my answer. Alright, let's use that same equation, but this time let's prove that negative 5 is a lower bound. So I'm still going to do synthetic division with that number. And if you look, my signs here, they alternate. I go from positive to negative to positive. And because they alternate signs, that proves the work here is what proves that negative 5 is a lower bound. And I know that's a lot, guys. Just remember, the majority of this is just using synthetic division. So if you're not sure what a specific theorem is, remember, you don't have to know the theorem, just understand how to apply them. And that is it.